Hello everybody. Today the topic of discussion will be the next design technique in algorithm design. Till now we have seen that the concept of algorithm design is that of generating an initial solution, which is a recursive definition to a problem, and then refining it. Among the refinement techniques that we have seen are two very important techniques. First, of balancing the split, and secondly that of dynamic programming, where identical problems are solved only once. Today we will discuss another very important technique, is that namely that of pruning. Now, pruning of a subproblem. Now, what do we mean by pruning of a subproblem? That is, while solving a subproblem, we will try and ensure whether it is at all necessary to solve that subproblem. Now, pruning can come in various ways, and one of the most famous techniques of pruning is the technique of branch and bound. It does not take care of all the types of pruning. There is another very important technique of pruning called the greedy approach, which essentially is related to the recursive definition itself. Therefore, if the recursive definition is correct, you can get a good greedy approach. You can have a look at greedy approaches in standard books on algorithm design. But as a process of refinement, branch and bound is one of the most well used and well studied techniques. It is specially used for solving problems which take enormous amounts of time and are applicable for problems which are optimization problems. Optimization problems are usually those which require minimization or maximization of a particular value. Sorting is not an optimization problem. Sorting is a problem where you are trying to obtain a sorted version of the solution. Therefore, an optimization problem is one in which you are interested in finding out the maximum or minimum value of a certain problem. Now, let us see what we mean by such a situation. So, the topic of today's lecture is branch and bound. But in order to understand branch and bound, let us pick up a problem and let us see how branch and bound technique comes up in solution to that problem. The problem, you will recall, we have done earlier, that is the stamps problem. In the stamps problem, you are given a set of stamps, a list or a set, S1, S2, S3, Sn, say. And you are given a quantity, value C. Now, you are to pick out a set of stamps in the solution. You are to pick out a solution which is a subset of L is equal to some x1, x2, xp, where each xi is an element of L and it's a distinct element. Let us for the time being say we are choosing one stamp can be taken only once, such that summation xi I equal to 1 to p is equal to c. And so this is a solution. You are picking up a set of stamps whose value is equal to c. And what do we want? And the number of stamps is minimized. That is, we want to pick out a set of stamps whose sum is equal to C, such that the number of stamps is minimized. So here we have an optimization problem at our disposal. The problem stated is as follows. You are given a set of stamps, you have gone to the post office and they said that, look, here are the only stamps that we have, and you've got a certain amount of space and you would like to fill up stamps of exactly a particular value, okay? And you are to choose the minimum number of stamps which meet this value. One version of the problem is choose a set of stamps which meet this value, but that is not an optimization problem. A minimum number of stamps which meets this value is an optimization problem. Let us take an example, and that will help to clear the air. Let L be 6, 5, 4, 3, 2, 1. These are the set of stamps, and I can take each stamp. This is the value of each stamp, and I can take a stamp only once, and the C is equal to 9. Now I have various solutions. The first solution that I can choose is 6, 3. Second solution I can choose is 5, 4. Third solution I can choose is 6, 2, 1. So these are the solutions that I can choose. There is another fourth solution I can choose, 4, 3, 2. A fifth solution I can choose is 5, 3, 1. So these are the solutions which I can choose. Among these 5 solutions, it is easy to see that this and this both are the minimum quantity, because there you are choosing only 2 stamps. So how to find out a solution to this problem? It may seem natural that we sort the stamps and choose the maximum and choose the next one, we should be getting the optimal solution, but that indeed is not the case. Because if you are asked to choose a particular value, and it does not necessarily mean that if you choose the largest one, for example here you say I'll choose 6 and then I've left with 3, so 5 and 4 is not possible, then I'll choose 3 and here I get the optimal solution. Sorry, that is the case only in the scenario where you are given in a particular scenario. Maybe you will be given a different formulation of the problem where you will get a different solution altogether. For example, if L was given as 5, 3, 2, let's take 5, 4, 3, 2. L is 5, 4, 3, 1, 1, and let us say C is 7. Then normally we would say choose 5. Now you are left with 2, you cannot take this, you cannot take this, so you will take 1. Then again you are left with 1, so you will take 1. And you would end up with a solution like this, whereas the solution 4, 3 is optimal. Therefore, a simplistic approach like this, where you choose the largest and continue taking the largest element to meet your quantity, may not give you a solution. Therefore, you must be careful about solving the problem optimally. Therefore, a simple largest first approach will not give the solution. So, how do we go about solving a problem like this? Any problem, as we discussed before, in order to solve that problem, we need to provide an initial definition to the problem. And an initial definition is a recursive one. And we have seen such problems, we have seen the permutation and the combinations problem, and where we looked in at the stamps problem. And one recursive definition of the stamps problem is to work it out as we do, just as follows. To consider all possibilities, let us say we have got L, C, and N is the number of stamps taken till now. This is the number of stamps chosen till now. Therefore, initially it will be called with L and C and 0. Now what are the cases? If C is equal to 0, obviously I have found a solution, and the solution is N. Because if C is 0, the solution is N. So I return saying I will return with success. So I return with success means 1, and if it is successful, the solution is n. So I return a structure which has got 2 parts, 2 integers, 1 which indicates 1 or 0, 0 means failure and 1 means n. If this case is not true, else, so each case is else. If C is less than 0, then obviously we fail. That is, you have got a negative value to meet and it's not possible. So you return 0 minus 1. Similarly, if these two are not true and L is null, that is C is not 0, C is not negative, but L is null, that is L is null. There is nothing to choose from. Therefore C must, if it is not 0 and it is not negative, it must be a positive quantity. If C is positive and L is null, you have no stamps to choose and you've still got to get a value, again you will fail. These are actually all the base conditions of the recursion. Now if these are not 0, then obviously L is non-null and C is greater than 0. And as we discussed before, you have got 2 choices. Choice 1, if L is S1, S2 and say Sk, you have got 2 choices. One is choose S1, that is S1 will be in your solution, and do not choose S1. That is, either I can take S1 or not S1. If I take S1 and I am sure to take S1, then I will make L dashed is equal to S2 right up to Sk, C dashed is equal to C minus S1, and I will recursively call it, if this was stamps LCN, I will call stamps L dashed, C dashed, and since I have taken one stamp, N will be one more. So I will get a solution for this, and a solution for this will be say x1 n1. And if I do not take it, that is I do not choose the stamp, then obviously since I am not going to take it, L dashed is there, but C does not change because I have not chosen any other stamp. I have not chosen any stamp here. So I have just decided not to take S1. So in my new list L dashed, and N remains how many stamps I have already chosen. And suppose this gives x2 n2. So these are the only 2 options I have at my disposal. I can either take S1 or not take S1. I could have done it for any one of these, but I can just choose one of them and do it. There are other decompositions, but this is the one which we are taking. Now I compare these 2. These are the 2 recursive decomposed solutions that I have obtained. Now if both x1 and x2 are 0, then I return this. So if x1 and x2 are equal to 0, both, then I fail and I return minus 1, 0, minus 1. If x1 is 0, x2 is not 0, I return n2. If x2 is 0 and x1 is not 0, I return n1. These parts are clear. And if both of them are non-zero, that is this also gives the solution and this also gives the solution, then since I am choosing minimum, I will choose the minimum of n1 and n2. So to repeat the whole recursive, so this is how we do it. The recomposition step is based on these, the solution of these 2. That is, either it will be failure, or it will be n1, or it will be n2, or it will be the minimum of n1 and n2. Now if under failure, if you return infinity, then taking a minimum will give you the solution. Well, if it is 0 and you return infinity, then obviously taking a minimum of these 2 will give your solution, because if both are 0, both will be infinity, you will return infinity. Or any way you can solve the problem. So the steps are, these are the base conditions. This is the inductive step. And this is the recomposition. So if we write out the algorithm, then it will look like this. If C is equal to 0, return 1n. The failure cases are, if L is 0, that is, if this does not happen, the else part automatically starts. To save space in such a long definition, I have not written out the else part. If L is equal to 0 or C is less than 0, then you fail. And if these two are not true, you go into the inductive part of the whole definition. That is, these two are the base conditions, and from here you decompose. If L, let L be S1 to Sk, L dash is L minus S1, C dash is the value, you subtract the value, and here is the two decompositions. You write them in any order, it does not matter. So you will solve them both. Stamps on L dashed, C dashed and N plus 1. This is choose S1. And L dashed, C and N do not choose S1. And after this part, from here onwards, this part is the recompose. As we have already discussed the structure of the initial definition, if x1 is equal to 0 and x2 is equal to 0, return 0 minus 1. Else, that is, both are not 0. If x1 is alone 0, then return n2. Else, that is, x1, neither are both 0, nor is x1 alone 0, then x2 can be 0. If x2 is 0, then return n1. Now if none of them are 0, then you return 1, that you've got a solution. In both of these also you got a solution. And the minimum of n1 and n2. So this guarantees, because at every step the only two alternatives are choosing or not choosing. So you've taken care of all possible cases, and it is easy to give an inductive proof that this algorithm is definitely correct. So this is the initial recursive definition. Now let us solve the problem at hand, and let us see how the algorithm will proceed to obtain the solution. So let us take the problem that we were looking at, that is L and C is equal to 9, and we initialize n to 0. Now C is not 0, L is not null, C is not negative, so obviously the base conditions do not hold, and you have got two options, choose 6 and do not choose 6. So let this be choose 6. Let us work out, since the algorithm, let us assume that the algorithm will go in a depth first fashion. So there are two options, 6 is taken and 6 is not taken. If 6 is taken, C becomes 9. If 6 is 6, C becomes 3. If 6 is not taken, and N becomes 1. If 6 is not taken, C remains 9 and N remains 0. L dashed in both cases becomes 5, 4, 3, 2, 1. Recall, one is L dash C dash N plus 1. The other is L dash C N. L dashed in both, one is C dashed N plus 1, the other is C and N. So again you recursively call this one and this one. So this one would have given. You could choose 5 and you need not choose 5. If you choose 5, then C becomes minus 2 and N becomes 2. If you do not choose 5, then C remains 3 and N remains 1. Here, let us just work out the recursion tree and then we will see how the algorithm will work and solve it. Here again, if you choose 5, your C becomes 4 and N becomes 1. If you do not choose 5, C becomes 9 and N remains 0. And L dashed here in this scenario, L dashed is 4, 3, 2, 1. Now here obviously you stop because C is less than 2, negative, so you return, here you return 0 minus 1. But here neither is C 0 or negative and N is 1, so you've got the option of choosing 4 or not choosing 4. If you choose 4, you get C equal to minus 1 and N is equal to 2. Otherwise C remains 3 and N remains 1. Here, if you choose 4, C becomes 0 and N becomes 2. If you do not choose 4, C remains 4, N remains 1. Here if you choose 4, C becomes 5 and N becomes 1. Here if you choose 4, do not choose 4, C remains 9, N remains 0. At this point, this is failing, so it returns 0 minus 1. This one continues, and L here is 3, 2, 1. Here you may choose 3. If you choose 3, C becomes 0 and N becomes 2. If you do not choose 3, then C remains 3, N remains 1. Here you return with success because C has become 0. You return with 1, 2. And here again you will continue by choosing 3 or not choosing 3. Here you will continue by choosing 3 or not choosing 3. Here you will continue by choosing 3 or not choosing 3. And there are 2 more steps. Here you end it to 1 and you will have 2 more levels, one with only 1 and one with null. And this is how the recursion tree continues. And in each of them at the leaf node. So this is the structure of the whole recursion tree, and based on this structure let us see how our algorithm will proceed. In order to understand how our algorithm will proceed, let us put in this scenario. Here we will choose possibly first, let us say first we will do this one and then this one. We could have done any one of them earlier. That would have meant that here we will do, if we did this side first and choose first and not choose second in the recursion, then we would have written it this way. If we reversed it, then we would have done this side first and this side second. Now let us assume, and you will see it is practical to do this side first and this side second. Then in that scenario, how will the algorithm proceed? The algorithm will come here at this node, then it will come here. So first it will do this, then it will come here. At this point it will break up into these two, and due to the depth first nature it will come here. Once it comes here, it will backtrack back here because it ends here. Then it will come here. From here it came here, When it backtracks, it has returned this solution. So the value of x1 n1 here is this value, 0 and minus 1. Then it will come here. Then it will come here. Here again it will backtrack because it has failed, so it will come back here. Here, then it will come here. After it comes here, it will come here. Now at this point it has found a solution, so it will return 0 and 2. Now let us come here. Here we have come at a node. Now till now this is the first solution that I have got, and the solution that I have got here, that is, this will return 1, 2. Now let us analyze. At this point, till we did not get a solution, there was nothing to be done. But as we come here, we have got one solution, and the cost of that solution, that is the present best cost, is 2. It may decrease because we don't know, but in this solution, now when we come here, we have come to a point where we have chosen one stamp, and this is not a terminal solution. Therefore we will choose at least one more stamp. Now if we choose one more stamp, still we are not guaranteed whether we will get a solution or not. At this point you can argue in the following manner: if I continue below this, I am not going to get a solution which is better than 2, because I have already got a solution of cost 2, and there is no chance of getting a solution better than 2 here. Therefore what I can do is, I can simply say it's not necessary to go beyond this point. Therefore, other than these two backtracking conditions or the base conditions that we have, I can do what is called a prune here. Because what is meant by prune? I will say that if n in the algorithm here, this is one base condition, this is another base condition. At this point, I can say the following. What can I say? I can say at this point that if n, let us assume that the present best cost is a global variable. If n is n plus 1 is greater than or equal to the present best cost, simply return. I return with failure, there is no point, I will not get anything. The value of n plus 1 is greater than or equal to the present best cost. Look at the situation here. The value of n plus 1 is greater than or equal to 2, which is the present best cost. There is no point continuing here. So what I actually do is, here I just simply return. This is the pruning step. And when I do get a solution, here I update present best cost. When I get another solution, I will update the present best cost, because if the new solution is better than the present best cost, obviously I will update it. Otherwise, I will prune. So this is a pruning which will help to reduce the search which would have unnecessarily examined the whole portion below this. So here I prune, I come back here, I come back here, I come back here, I come here, I come here. Now what is the value of n plus 1? Is 1. So I cannot prune because n plus 1 is not greater than 2. Let us come here. At this point, n plus 1 is 2, I've already got a solution of cos 2, so there's no point continuing here. And look, even if there is a solution below this, I still prune and return 0 minus 1. Why? Because I know that whatever the solution, even if there is a solution below this point, that solution is not going to be better than the best solution that I have already got. Therefore, I will simply get out and come out. This is the pruning step of branch and bound. So now I'll come here. Once I come here, here again I cannot prune because n plus 1 is 1. But once I come here, I will prune, get back, I'll come here and again continue. But notice that those portions like this, below this, whatever I could have seen is a big tree, 2 more levels was there, I did not see. All these portions are pruned, which normally an algorithm would have done. Below this I do not see, and I continue below this, and you can draw up the whole search tree to see that a lot of things will actually not be examined. So this is the idea of pruning. Now this pruning depends on the direction. This sort of pruning in a minimization problem is called the depth first branch and bound approach. This idea, since we are doing depth first search, going down like this is called depth first branch and bound. What is meant by bound? Branch is this branching, bound is I have got a value and I know that I can bound my cost by the value. For example, here I can bound it by n plus 1. I know that the solution is bounded by n plus 1. It must be more than n plus 1 at any point which is not a goal node, which is not either C is not equal to 0 or C is not negative or L is not null. I am definite at this point that the solution cost is greater than equal to n plus 1. Therefore, that is the bound which I use with my present best cost. Therefore, what I do in depth first branch and bound for the stamps problem, I keep a global present best cost, initialize to infinity or to the total number of stamps, whatever, any upper bound, and then in the same thing I use the pruning step. What is the pruning step? If bound this is in a minimization problem. I leave it to you to understand what will be in a maximization problem. If bound value is greater than equal to present best cost, return. So based on this concept, you need not go into the decomposition step. This will be just after your base conditions prior to decomposition. And in the base condition, if solution found, which previously you were returning the value, you will update the present best cost. So these are the two additional things that you do in the initial recursive definition. And once you do these two additional things, you are sure to reduce your search to a large extent. So this is the essential philosophy or the idea of branch and bound. The idea of branch and bound is, in the initial definition, you try and examine, this is especially applicable for optimization problems. In a minimization problem, you will define a bound which guarantees that the solution will be greater than equal to the cost at this point. In the stamps problem we have seen that if the base conditions are not true, n plus 1 is a bound. That is whatever number of stamps you have chosen till now, one more stamp at least you are going to require, because you have not yet reached the solution. Now if that bound is greater than equal to the present best cost, there is no point decomposing, generating sub-problems and trying to solve it from there. On the other hand, if it is not so, you have to do it. So, but if it is so, you will reduce the search and prune to a very, very large extent. And you can work out the complete stamps problem. You can start the depth first from any other direction and see. In a maximization problem, and you can look at problems of maximization, there, since you are maximizing a value, you need a bound which is an upper bound. That is, it should be saying that the solution will be no less than this. And you will prune if the upper bound is less than the or equal to the current best, because the current best will continue increasing. In a minimization problem, the current best will continue decreasing. In a maximization problem, the current best will continue increasing. This is the concept of depth first branch and bound. There are other branch and bound techniques like the best first branch and bound and other variations. Therefore, like dynamic programming where identical subproblems are done, like the balancing where the split is to be done, branch and bound is one of the foremost techniques of algorithm design. Therefore, it is important. We are not going to detail out the properties, the formal properties of branch and bound. You would do it in an algorithm design course. But here, where we are doing programming methodology, our idea is from the initial solution there is a concept of refinement, and this concept of refinement has got various aspects, and among the three well defined aspects in algorithm design, one of them is definitely branch and bound. So we have just done a flavor of branch and bound to indicate how to obtain solutions, and you will use them in various problems, especially graph algorithms and other problems where optimization, that is minimization or maximization, is effectively required. Thank you.